Christian, would you like to say something briefly about TECSUD?
Yes,
No?
yes.
Yes, would you like
yes.
to start off and just introduce TECSUD?
Yes, perfect. Okay, my name is Christian Castañeda, and we have been working with TECSUD about 8 years. TECSUD is a company with more than 20 years in the market, in the different markets. Specifically in mining, we have been working with Olympus and XRF technology. Now we are the representative of Geotek for Colombia and Ecuador. About 1 month, we are working together with Geotek, and right now I am the product champion and the business developer of Geotek in TECSUD for Colombia and Ecuador, and we are very happy to work together with Geotek.
Thank you, Christian. My name is Marcus Lake. I'm the Managing Director of Phoenix Mining Technologies. I've been working in XRF and XRD for 13 plus years, and in my previous role with Olympus, obviously working with TECSUD very closely in XRF and XRD. So I've known TECSUD for a very long time. My role now with Geotek is to be their mining representative across the world. That's my general background. We will be providing a copy of this presentation for everyone for afterwards. We look forward to showing you Geotek's equipment. Over to Alice.
Okay, great. Thank you, Marcus. So hi everyone, my name's Alice. I'm the technical sales geologist at Geotek Limited. So my background is obviously in geology, and I've been working for Geotek for the past couple of years, working with MSCL technology and X-ray CT technology as well. So if I could just ask for the next slide, please, Marcus, and I'll give you all a quick introduction to Geotek as a company and what we do. Okay, great. So Geotek Limited specialise in the development and manufacturing of multi-sensor core logging technology. We call this MSCL for short, and then X-ray CT scanning systems. And we've been doing this now for about 25 years or so. So founded in 1994, Geotek actually sold its first MSCL system to the USGS, so the United States Geological Survey, and it actually housed P-wave velocity and gamma density. However, since then, we've actually broadened our horizons to supply a range of different instrument and sensor technology. So this has enabled us to branch out from predominantly the research and academia markets to other fields such as the oil and gas markets, geotechnical, and more recently, the mining and mineral exploration sectors. So as you can see just from the map here, we've sold our equipment to a global customer base, having sold more than 240 systems worldwide. But this isn't only for purchase. We also actually offer our equipment for lease and services. So by that, I mean customers can send cores to our labs in the UK and we can scan the cores for them. Or we can actually take our equipment to remote locations or offshore locations for offshore projects and actually log the cores on site. So if I could just ask for the next slide, please. Okay, so here we have some examples of companies which have either purchased equipment from us over the years or have worked with us on servicing projects. So as you can see, our customer base is predominantly still in the research and academia field. However, now we have many clients in oil and gas and mining and mineral exploration sectors, as I mentioned. Clients in South America, I should say, include, for example, Inocar, oil giants such as Petrobras, and large-scale mining companies such as Vale. So if I could just ask for the next slide, please, Marcus. Okay, so before I hand back over to Marcus, I just wanted to leave everyone with the question of why do we actually do core scanning in the first place? So I'm sure you're all aware that core is very expensive to extract in the first place, but it is the only way that we can physically observe what's going on in the subsurface. So we like to think of it as the essential ground truthing that gives us a clue into the underlying stratigraphy. So as you're also probably aware, core is often destructively tested, particularly in the mining and mineral exploration sectors. However, we think that there's a plethora of information that's just being missed here. And so we're not fully utilizing our core samples. So Geotek actually offer an attractive solution to this through non-destructive, high-resolution, semi-automated logging. And on that note, I will hand over to Marcus to introduce you to our box scan system.
Thank you for that, Alice. So what we will be doing this afternoon is presenting a few solutions from Geotek. The main one, obviously, being my focus is their newest, latest product, box scan. I wouldn't say a more simplified version, but just an easier version with less sensors that are known to the mining industry. So on the left-hand side, you'll see box scan 1. This was the box scan that we launched earlier this year at the PDAC event. As you can see, if we use our imagination, it's quite large. It fits normal core trays. On the right-hand side, what you'll see is a mock-up of what the production box scans will be. We took notes from the industry on size. As you can see, it'll have a tray that goes up and down, and we've repositioned the height and size of it for freight and transport on normal commercial airliners. The original model, we couldn't fit on normal airliners. So we've taken some advice from energy, fully ruggedized. Weighs about 300 kilograms and will fit on the back of a pickup or truck. So fully transportable, fully ruggedized. Geotek's background, they've done a lot of work in offshore labs. So they are very used to rugged environments. So what does this box scan, what sensors does it have on it? So if we go from left to right, have a close-up of the sensors. The first sensor is the Vanta portable XRF, which does chemistry. Second sensor is the Malvern ASD lab spec or TerraSpec, so it's hyperspectral. The little white box in the middle is magnetic susceptibility, does magnetics. The little square, sorry about that. The little square box on the arm, that's a laser profile, a laser aligner. I'll get back to what that does shortly. So that has a dual function. And then on the right-hand side of the robot arm, we have a high-resolution camera, line scanning camera. So all those sensors are integrated onto the system. Alice will explain how the integration works later on in the presentation. But as we would know, the Olympus XRF does chemistry. This does mineralogy, the ASD, magnetics, laser aligning, and high-resolution photography. So this all comes together in a depth co-registered manner. As you can see on the right-hand side, it provides a whole host of data for the operators, for their core. So we are bringing some very interesting, innovative software packages on board and in the cloud for this equipment. For the mineralogy spec and the AI Cirrus products. So Ozspec was recently purchased by a company called Index, which is a very large drilling services and technology company, which most people in the mining industry are very familiar with. So from the hyperspectral data, our customers put that data up to the cloud and in comes back interpretive hyperspectral data for the customer. so they don't actually have to interpret hyperspectral data on their machine. As I mentioned, the laser aligner is actually a mini LiDAR, and from the laser data and the photographic data, we are working with a company called Data Rock. Everyone afterwards can go and have a look at this link. And we're getting a whole host of very, very interesting, innovative, derivative data sets, block detection, optical character recognition, driller's breaks, segmentation from the point cloud, fracture models, edge detection, detection of planar exposed surfaces. So if you can imagine, as you can see in that small photograph there on the left, you can see ellipses, it picks up the writing on the boxes, from, tos, and a whole host of data. So this will also be cloud-based. So companies will be putting the data up to the cloud and getting some very, very cool, innovative products back to the system overnight or almost in real time. So what does that actually provide for the customer? Here's an example of the box scan data set. As you can see, it's all depth co-registered. On the left and the right, you'll see we've got the line scanning photograph. Should be noted the line scanning photograph, our native resolution for line scanning photograph for the box scan is about is 50 microns, but it can be run at a lot higher resolution. So as you can see here, there's a calcium-rich layer from 55 to 65. As the color changes, there's a drop in aluminium, silica, iron, and potassium with an increase in calcium. Multiple veins seen in these examples are shown quite clearly in the high-resolution line scan image. You can see through here the change. Iron and potassium contents correlating with magnetic susceptibility data along here with the iron magnetic sus. Downcore high-resolution image spectrometry point magnetic susceptibility and XRF data. So as you can see across the top, color, magnetic susceptibility, aluminium, calcium, titanium, iron. So this is just 4 elements chosen here along with the high-resolution camera. We are able to zoom in on these photographs as well with the client. Moving along. So here's a log image of our the correlation between our ASD, mineralogy and chemistry, and magnetic susceptibility. The mineralogy and chemistry identifies the carbonate-rich beds that the high iron content is predominantly associated with, the chlorite-rich intervals, which also have very high magnetic susceptibility, suggesting presence of magnetite. So as we can look across here, we can see it's all depth co-registered as well. What other data sets can we provide with this system? So what information can we generate from a combination of downhole data sets from the box scan? Here we are looking at intrusive volcanic sample. As you can see that the iron content is increasing in the X direction as compared with the other elemental data in the Y axis. By combining our XRF data with our mineralogy from the ASD, we have conclusively grouped our data points in 2 units. Chlorite-rich data points with high magnetic susceptibility, magnetite, that's in the green, and carbonate-rich data points, blue. Within the sample, areas where lower iron concentrations were detected by the XRF, we have found high calcium and were identified as carbonate from the ASD data, where iron concentrations were the highest. A range of calcium and silicon concentrations were recorded and chlorite was identified in the ASD data. The ASD data exhibits a strong, clear, shortwave infrared response with the identification of chlorite and carbonate. No visual near-infrared minerals were identified in this sample. high abundance of iron was detected by the XRF, and high mag sus points were recorded by a point magnet susceptibility sensor, indicating a highly magnetic mineralogy. We can see that in areas of increased iron content, we see highs in the magnetic susceptibility values, as you would be expected, and then show the correlation. Combining the results from the ASD and XRF allows for the identification of chlorite as the iron-bearing minerals in this sample. This is supported by the mag susceptibility data, where magnetic susceptibility is higher, chlorite, iron-rich, is present where the magnetic susceptibility and lower carbonate is present. The very high readings from the magnetic susceptibility also strongly suggest the presence of magnetite. The slide highlights the benefits correlating to the different data sets to achieve geochemically reliable results. So, as you can see, when we combine data sets downhole with XRF data and mineralogy, we can get mineral groupings for the customers. As you can see in this slide here. It should be noted that this system, we believe, we can get about 800 shots in a 12-hour shift. So that could be 1 shot per meter. Someone came in. Let me stop. Let someone in. So 800 shots in about a 12-hour shift. The device that slows the box scan down is obviously the portable XRF. So 800 shots, we're running the portable XRF at about 30 seconds. So all of you can do the maths on how much core you can get through in a 12-hour shift. As I mentioned by Christian, we'll be happy to talk to you all after the presentation about testing times and other outcomes for the box scan. Now I'd like to pass over to Alice for the presentation on the larger multi-sensor core logging platform, the MSCL.
Okay, great. Thanks for going through the box scan there, Marcus. All very, very interesting data. So now I'd like to introduce you all to the concept of multi-parametric scanning through the Geotek multi-sensor core logging systems. So as I said, we call these MSCL. So as mentioned earlier, Geotek design a range of different multi-sensor core logging platforms that cater towards different industries or different applications. So the great benefit and I guess uniqueness of these systems is that they offer a way of obtaining multiple down-core data sets at once. So rather than just acquiring data regarding magnetic susceptibility, for example, you may scan the core for a range of different parameters. This can include geochemistry, like Marcus just explained regarding the box scan, or it can include geophysics as well, or a combination of the both. So in the upcoming slides, I'll go through some of our sensor options, but I just wanted to reiterate here, I guess, that the reason for this type of scanning is to acquire that high resolution data set of multiple parameters at the same depth, which subsequently enables you to explore parametric relationships that might have previously been hidden in, I don't know, purely visual identification, for example. Next slide, please. Okay, so this is our MSCL S. We call it our standard multi-sensor core logging system, as you can see just in the image there. So it's our most versatile system and semi-automated core logging platform. So it's able to analyze cores of up to 1.5 meters in length and up to 15 centimeters in diameter, with a variety of different sensor options installed. So this may be based on client desires or project requirements. So the system's able to take simultaneous measurements and obtain depth co-registered down-core profiles at various intervals. So the measurement interval, which is where you actually take the measurement on your core sample, may be selected based on project requirements, but it's typically in the range from millimeters to decicentimeter scales. So the flexible geometry of the MSCL allows for a range of core to be selected and actually scanned. So this can be whole core, it can be split core, it can be hard rock core, or it can be sediment cores within plastic liners, for example. So the client can really pick and choose their desired parameters, again, probably based on project requirements, and a typical setup allows for geophysical measurements and geochemistry to be conducted, as I said, on a variety of core samples. And this can cater towards a range of different applications. So this could be interpretation of lithology types, it could be estimation of down core stratigraphy, it could be core-to-core correlation, and it can even be just looking at physical properties like bulk density or porosity. So how the system essentially operates is that the user would load the core on the right-hand track and then essentially tell the software to go, and the core simply translates through the system, through the sensor options, and then the user offloads the core on the left-hand track. And you can do this continuously to allow for continuous 24/7 scanning if your project is a continuous project, or you can simply turn the system off after an 8 or 12-hour shift and then come back to it the next day. Next slide, please, Marcus. Okay, so as mentioned, Geotek offer a range of different geophysical and geochemical sensor parameters, and these are all able to be integrated onto our different MSCL platforms for depth co-registered simultaneous scanning. So the customer may be able to choose their desired system, for example, the MSCL S, which we have in this image just here. And then after they've chosen their system, they can choose their desired sensor options. So all our MSCL systems are modular, meaning it's easy to integrate and customize your sensor options. So this also means that the client's able to customize their MSCL system by either upgrading sensor options later on or simply adding sensors to the system if they're needed. So we offer up to 11 different sensor options, and we like to usually group these into geophysical and geochemical sensor options. So we have our geophysical ones like gamma density, P-wave velocity, non-contact electrical resistivity. We have magnetic susceptibility, a loop and a point for whole core and split core. And then we have our total and spectral natural gamma. So those are our geophysical property sensors. And then we have our geochemical and spectroscopic sensors. So we have things like color spectrometry, we have a very high resolution line scan camera, and then we have XRF. We have two different types. We have the Olympus Vanta, which is able to be detached from the system and used in the field as well. And it's also able to be used on the system, obviously, for core scanning. And then we have the high resolution Geotek XRF, which is for very high resolution lab results. And then we have our hyperspectral systems. We have the ASD spectrometer, so looking at mineralogy. And then we also have the SpecCam 4 hyperspectral camera, also looking at mineralogy in the short wavelength infrared and very near infrared. So essentially the main goal here is to combine these sensor options onto one system to acquire simultaneous results and hence extract the most information we can from our core sample. Next slide, please. Okay, if you could just click through the animation, Marcus, sorry. One more time. There we go, thank you. Okay, so here we have a case study example of more than 40 feet of core. So this is from the Osprey field as part of the Dunlin field decommissioning program. Geotek were actually given this core sample. So this is from a borehole that was drilled, as you can see, in 1985, and there was actually wireline data collected on this borehole. So Geotek scanned this archived core to see if we could actually achieve a better understanding of the stratigraphy happening and achieve a higher resolution data set and compare it to the wireline data. So in this case study, we're looking at interlayered sandstones, shales, with the occasional siltstone, I think you can see here. But what you can see here is that the original wireline data seen in those long dashed down core profile lines looks at properties such as natural gamma and P-wave velocity, as you can see here. And then we have the MSCL data sets, which are the finer resolution lines moving down the core there. And so what we can see here is that there's actually a very good correlation between the well log data and the MSCL data. However, the MSCL data actually offers a much finer measurement interval and therefore a greater resolution, which means you can really pick out the highs and lows of the data, which you wouldn't otherwise see in the wireline data. Then we have the added value of the geochemistry. So looking at all this XRF data we have on the right. So this was all collected through the Olympus Vanta, I believe. So what we found from analysing the wealth of MSCL data that we have here was that due to the finer resolution from the MSCL dataset, we were actually able to indicate additional geological boundaries that weren't actually present in the wireline dataset. So for example, we have the identification of some iron-rich beds. So if you just look in the XRF data here, just in orange, you can see some areas of very high iron content. And then if you follow that depth along, you can actually see a very high magnetic susceptibility over on the left-hand side and a high gamma density and P-wave velocity. These are all very indicative of a high iron-rich bed. And you can actually see this at multiple different intervals as we move down the core sample. So as I said, these beds were not identified in the visual logging or initial wireline data, but may prove potentially very significant because they were not previously identified. So this example really just highlights that through this type of multi-parametric scanning, you're able to compare properties and explore those relationships, which may lead to, in this case, the identification of additional beds that weren't previously identified. Okay, so if we can just move on to the next slide. Okay, so here we have another example, which is a combination of geophysical and geochemical parameters through the MSCL. If you take a look at the black dots we can see here in some of the left-hand columns, these are actually lab measurements, so taken from discrete lab sampling. And what we can actually see here is that the continuous nature of the downcore MSCL data not only correlates with the lab tests, so I should say that the downcore MSCL data is the very colourful downcore profile lines we have here. So it not only correlates with the lab data, the black dots, but it also adds significant value to the discrete lab data, enabling the user to identify detailed centimetre scale differences in the stratigraphy. So combining the geophysical and geochemical data sets from the one system, the MSCL S, enables us to unravel a complex geological strata to get a better understanding of the geological history here. So as I'm sure most of you are aware, carbonate minerals such as calcite and dolomite are composed mostly of calcium and magnesium. However, dolomite contains more magnesium than calcite. So the XRF data here actually shows the ratio between the magnesium and the calcium in these carbonate rocks is relatively consistent as we move down through the geological units. So this implies the ratio between the dolomite and calcite is probably consistent as well as we move between the two units, which is important as dolomite-rich rocks are typically denser and stronger compared to calcite-rich rocks. So the client from this example originally thought that the change in density, so the left-hand column here, as we move down the core was a factor of chemistry. So the client thought that we were actually changing lithology types to something that was more quartz-rich or silica-rich. But actually, the MSCL data told us otherwise, and we now understand the MSCL data has given us a clue that this is actually a factor of carbonate diagenesis as we move down the core sample. So that's actually the reason for the density change. So I think the density change is just at about 13 meters there, as you can see from the box. We have a high density in the upper unit and the lower density in the lower unit, and we have now discovered this is due to carbonate diagenesis. So this essentially means that we're able to show and use MSCL data to define the stratigraphy. So in this particular project, it was the only way to correlate between boreholes, as the visual observations don't actually discriminate between the two stratigraphic units. So in other words, the core all looked the same, but the MSCL data proved otherwise. Okay, if we could just move to the next slide. There we go. Okay, so now I'd like to introduce you to our SPECCAM 4. So this is our relatively new short wavelength infrared, very near infrared spectrometer as of 2019, and it's used for mineralogy interpretation. So for those of you that aren't very familiar with hyperspectral cameras, how it works is essentially it looks at the different absorption bands given off from the minerals within the core, and this corresponds to certain mineral types. Now we offer, with the purchase of the SPECCAM hyperspectral camera, we offer a dedicated mineral library. So in this case, you can essentially semi-quantify your core mineralogy. So the software essentially identifies minerals semi-automatically. So the sensor was developed through SpectraMap for, well, to produce two different types of deliverables, I should say. The first, so if we just look to the right-hand side of this slide, the first is a mineral map, in which case you can actually highlight your mineral of interest and look at the spatial distribution of that mineral within the core sample. So in this case, areas of red and yellow are high mineral content for whatever mineral it is that you're looking at. And then we move down into greens and then blues for low mineral content. And then the second deliverable is a down core, either part per million or percentage profile of that mineral of interest. So you have the mineral maps and you have the down core profile. Now we often find that this hyperspectral camera, along with our ASD mineralogy sensor, is often very useful when used in tandem with things like XRF, so looking at your elemental data, and then magnetic susceptibility, color spectrometry, and of course, high resolution line scan imaging. Next slide, please. Okay, so again, here we have a data example of our mineral maps. So on the left-hand side, you can actually see, on the right-hand side, you can actually see the down core mineral profiles here. So this is in percentages. We have illite, chlorite, mica, kaolin, and then we actually have total clay content and dolomite as well. And then on the left-hand side, you can actually see these mineral maps. So on the far left, we have a false color image from the hyperspectral camera. And in the center image here, we have percentage of chlorite distribution. So as I said, areas of red are high chlorite content, moving to yellows, to greens, to blues. And you can actually see, if you compare the chlorite content to the chlorite percentage profile, as you move down core, you can actually see where the chlorite increase is at about just under 7,117 meters depth. Okay, so now if we move on to the next slide, now I'll just show you a quick example of why hyperspectral technology is so useful. So if you can continue to go through the animations here, Marcus, and one more time. Okay, so here, what we're looking at essentially is an oil saturated sand core. So the image on the far left, the black image here, is a visual image. So this is a high resolution line scan, and this is of a sand unit. So as you can see, not a lot going on there. I can't see any bedding, I can't see any cross bedding, I can't really see anything. I might call it a massive sand. But then we use the hyperspectral camera and we look at the false color image. And then you can see, wow, there's loads going on here. You can see cross-bedding, you can see laminations, and you can actually, in this example, see biotubation. So you can see some of the burrows through those kind of semi-vertical burrows here. And then if you look at the next image, the third one along, we have the hydrocarbon content. So areas of high hydrocarbon content in red, moving to yellows, to greens, to blues. And what we can actually see here is that the hydrocarbons are actually infilling some of these burrows. So you could theoretically make an interpretation to say that the hydrocarbon spatial distribution in your reservoir, this was taken from a reservoir obviously, may actually be a factor of biotubation. So that's very important in this particular example. And in the image on the far right, we have clay content, total clay content. And you can see the areas of high clay content in red are areas of lower hydrocarbon content, which in this case would be expected, as you'd probably expect more hydrocarbons in the sand unit. So just a nice little example to show you how useful the hyperspectral and mineralogy data can be. Okay, so if we move on to the next slide. Okay, so we've gone through how we acquire our data, but how would this fit in a typical core workflow? So I've just got an example workflow here from a core repository in which we want to employ a range of different suitable geological equipment, so MSCL systems, including the box scan or the MSCL S, whichever one the client sees fit for the project. And we want to use these to non-destructively quantify and understand our geological stratigraphy. So firstly, we'd probably have our whole core characterization. So we'd probably have this on the box scan. So we load our core tray onto the box scan for geochemical analysis. And then we might think, okay, I'm interested in structural analysis. I might want to X-ray my core samples if they're not fragile core samples. And I should say at this point, Geotek do offer a range of X-ray CT scanning systems. So obviously you don't have to X-ray your core, but in this particular example, it's quite a useful step to get your structural analysis. And then we move on to physical properties. So looking at the geophysical data from your core sample, things like bulk density, P-wave velocity, electrical resistivity, and natural gamma. And from there, we're left with a wealth of information that we want to process and then essentially feed into some sort of database or somewhere secure that we can keep our data and view with ease of access. So this leads me on to our next couple of slides. Okay, so once the data's been collected, as I said, the user will want a secure place to store that data and potentially combine that data with other data sets like geological maps, wireline data, lab data, all your geological data. You really want that in one place for comparison with one another. So this is where the Geotek Atlas software comes in. So this is a cloud-based application and database server offering cutting-edge core visualization that supplies a series of customized modules, enabling seamless navigation through huge volumes of data. So as I said, you can combine your MSCL data or your box scan data with other data that you might have collected. You might have collected wireline data in the field, or you might have collected data from geological maps, for example. So this enables multiple data sets to be viewed alongside one another and actually visualized with other geological data sets. So this in turn enables the user to easily navigate through data sets or indeed create customized exports for reports. So if we can move on to our next slide. Okay, so tools that could be integrated into this Atlas software. As I said, you can integrate a lot of your existing data already. It's easy to integrate into the Atlas software and combine, like I said, with that MSCL or box scan data. You can combine it with Geotek X-ray data, so radiographs and CT, computed tomography scans. But what else can you combine? Well, you can combine data matrix tools, you can combine GIS tools, you can combine even search tools, but also you can combine things like machine learning as well. And we've actually had a recent study into this that I won't discuss the particular clients in this case, but yes, you can even add in machine learning, which essentially takes your semi-automated platform and makes it a much more automated system. But that is a sort of future development. So this Atlas software is really a powerful visualization tool, I should say, and a way of combining all your data sets into one unique place. Okay, so if we could just move on to the final slide that we have here. And I just wanted to end on a note to say that all of this is to extract, as I said, the most data you can from your core sample. And we do this non-destructively and with very high resolution. So we like to say here at Geotek, if a core is worth taking, it's worth logging. And on that note, I'd really like to thank Marcus and Christian for going through this presentation and organising it. It's been really lovely to share all of this with you. And I guess I will hand over to Marcus and Christian for an end note, and then I think we'll open up for questions.
Awesome. Thank you, Alice, for very detailed